Okay, so I'm going to give you sort of expand a little bit more what James was touching on earlier and update you on what preparations have been undertaken at ESA, particularly the last 3 years. So it's basically an overview of the development activities in the last E3P period. And it's several activities that were initiated and informed by responses from you to 3 open calls. There was one about lunar exploration, science and technology payloads, one exploring the moon with a large European lander, and a reserve pool of science activities for the moon. So this was what we were collecting the information on and initiating some new activities. So just to go back to that first call of 2019, the aim around that one was to gather information on the European science payloads as part of the program period, as part of a lunar mission campaign. And it's been a really great outcome. So over the last 3 years, we've been developing some European payloads that are developed now for flight implementation to imminently fly soon. So we have the exospheric mass spectrometer. So it's really going to help with detection of lunar volatiles. The PI is in the UK, and this is already going to be flying soon on NASA CLIPS, and is also being developed for JAXA LoopX missions as well. There's the Moonlight Laser Retroreflector. So this has then taken us into another field of science, really precise measurements for general relativity, geophysics, and Earth-Moon dynamics. And this is another CLIPS payload for the period 2024. And then there's another activity, sort of international collaboration with China, the Chang'e 6, the negative ions of the lunar surface. That's really looking at surface-bound exosphere dynamics and interaction. So really hitting different expertise and skills that are representative of the European community. We then had another call, and that was looking at exploring the moon from European landers. So we had the concept of the EL3 that's being called the Argonaut now. And we really wanted to build a portfolio of science mission concepts that can help inform that lander design. It's going to have multiple types of uses, but we want to make sure that any way that it's designed and developed does not preclude good science happening. So it was really important to understand what kind of themes and use cases could be around this lander design. And importantly, we conducted a lot of studies, both internally and with industry, but importantly, it was all done in consultation with different groups in the community. So whether it's through themed workshops or topical teams, we really appreciate all of the inputs and the science guiding that. I'm going to, into interest of time, flip through some of this, but just to let you know the diversity of what was studied, this was all at mission concept levels, informing the lander, as well as looking what would a facility, if you like, a payload package of instruments look like that could really start to inform the technical developments we need to help to be able to create flight opportunities and integration. So you can consider looking at the surface and environment, really looking at the dynamics of the space surface environment and understanding planetary bodies. But importantly, this also prepares for sustained exploration and helps really monitor the impact that we as humans may do during exploration. So such a facility there includes a concept in the bottom here. So we're really looking how would you perhaps use the concept of static lander to do these 3D measurements of electric fields and plasma and really understand what's happening there. We sometimes call this a little bit the Christmas tree approach. This is very science driven. So next stages would be, how would you prioritize this? How could you get this to a deployed facility? And this is where we need continued interaction with yourselves. We've done similar things with the biological sciences. This is a real key area if we're starting to look at sustained presence and getting humans further. We need to understand the environments that we're putting humans and the way we're going to sustain them as well, whether it's through other bioorganisms. So mission concepts were studied here, while looking at how you would use the static lander, but also looking at perhaps an early facility, really expanding from what we already know from the low gravity environment that we've worked on in the ISS, and really looking at in situ analysis and not only relying on the return of samples to analyze them afterwards. So we're starting to build the capability, the interest here, and understand what's the technology you need to develop these capabilities to enable the good science that you do. Similarly, we've been looking at mobile explorations, these like with a focus on geology, and several of these concepts that were studied as mission concepts have been presented here previously by the scientists at ELS. And we looked at really pushing the range, the duration, and the different types of terrain, but by looking at these different concepts, whether it's going to a regular Mare patch or looking at something ambitious like a 900-kilometer traverse across the Imbrium. It's driven by a science interest in studying the history of the volcanic and thermal history of the moon, but all of this leads to learning of the properties of the moon itself and how we may utilize this responsibly in the future. In the bottom right here, we have concepts of how you might use a reference set of instruments to do such exploration. And we did a similar thing looking at a more polar region, different thermal regime, different illumination, understanding what are the different types of challenges that you would encounter there. Again, using these reference facilities of instruments defined and described by yourselves as the instrument PIs, and looking what this really means. And we use concepts that have been published, for example, this Flahout et al. Concept here. So we're really looking at how do you interact with and deal with the radiation environment? What's the feasibility, the systems, the technology you need to be able to interface and integrate these potential science opportunities. Well, I said there's other ideas in there as well. So we have geophysics we've been looking at. Interesting around this, we looked a little bit at the drivers behind geophysics. You're really looking to be targeting longer durations than perhaps a static lander could support. So now you start to look at what would a survival pack, solar panels, batteries, communications, how does that all work? And how do you do that without then interference in the science data that you need? So we really started to look into this idea as well, preferably with the vision that you'll be able to start building up an international global network of these stations, perhaps contributions with international partners. And astrophysics as well. We did the far side of the moon's perfect radio quiet for really pushing that last frequency, that boundary. So we started to look at what could a precursor antennae look at to really assess the environment, the radio environment, the interaction with the ground before we could start to scale up to this concept of astronomical lunar observatory, which again, another study that has been conducted, looking how you would achieve the science and build up to such a scale, and that's been really driven by the inputs from the science community there as well. And then there was a third call as well, and this is the more recent one called a reserve pool of science activities for the moon. So all these kind of building up to payload facilities, building up to mission concept, you need to start somewhere. So we're starting to look at these near-term opportunities, look at the individual payloads that are out there that can be developed relatively soon within the next 3 years of identification of flight opportunity. And we got a brilliant response to this. And we have now finished our selection process. And we now have a brilliant reserve pool of 21 payloads that really represent European science as multidisciplinary, that is able to respond to the diverse different types of mission opportunities that could arise globally on the moon, different boundary conditions, perhaps with mobility, perhaps not with mobility, and really creating opportunities moving forward. It does remain to be said that it's not a guarantee to fly if you're in that pool, but it's a good start for getting the next few years going. So what does it mean? So all of that work, as James said before, there's no way we could move forward with everything, but we have learned a lot from the science, from the technical level, from the implementation, from the challenges that need to be addressed. So we're going to utilize those lessons moving forward, but we're going to frame it now in the scope of a new size-based strategy that we have within ESA. And that has a prioritization principle that says science as an enabler of sustained exploration. So this is including perhaps really focusing perhaps in on lunar environments and conditions. This we need for fundamental knowledge, understanding this tenuous exosphere that we have before we as humans go there and perhaps damage and impact it. And what are the impact it has on human beings and organisms and life support that's going to be needed there. In turn, we're driven by the curiosity of what else is out there. So we're going to look at life in the solar system, understanding its origins and its conditions. So maybe looking for the sources and history of volatiles amongst that. That in itself then can be used as perhaps a resource. We can look at different types of prospecting, seeing, we had a question earlier about commercial applications. Maybe we can create a commercial interest in that sense, but importantly, want to make sure that whatever we do is done in a sustained and responsible way. And overall, we just want to be creating opportunities for new scientific research, even if it's not necessarily the first driver as part of the Human and Robotic Exploration Directorate. And in the process, all of this is helping to address challenges that we find here on Earth. So we're going to achieve this in the nearer term with these contributions to partner-led commercial and perhaps some of the early Argonaut logistic missions, but that'd be a secondary passenger initially. But then we can build up to contributions and participation to Artemis crewed missions, and then perhaps more towards the mid-2030s timeframe. This is when we can start to use Argonaut for dedicated science application, harboring everything that we've learned in the last period, and will continue to do so.